4 says to add up those individual masses together. 5 says to take an average. How much does 1 penny weigh on average? So you take that collective mass and divide by 5.
Yeah.
So determine average mass.
Yeah, so you can't do it now.
So it's going to be average as your collective mass, the mass that you weighed all 5 of them together, then divide by 5. Right, yeah. When you're doing the average, you're not using your sum, you're using that collective mass where you measured all 5 together, okay?
Is independent variable the right word for something that, for like if the air pushes on it, it's an independent variable, right?
Yeah.
Okay.
Yeah, we try and control as many of those as possible. We want the only thing that's different is penny to penny. We want
AC
everything
is
else to be the
pumping
same
it
as much as
through.
possible. Yeah, that's why we have all those little doors, right? Because if you close all those, that prevents the air currents from pushing on the balance
Didn't
band.
do
So
that, so that's what I'm.
yeah, the
That's
other
my
the other
independent
problem,
variable.
and we'll talk about this, is if you notice when you were writing and you were pressing on the table,
Oh, yeah.
that makes the balance
Yeah.
fluctuate. Yeah.
Yeah.
All right. So hopefully you guys have done your mass and your sum and your average. So a couple things about our balance room that you may have noticed. The AC is pretty strong in there. That's why we have all those little doors on there, so those air currents that are coming in aren't pressing on the balance. But what you may have noticed is if you were writing on the table, like pressing into the table, you may have noticed that the balance was fluctuating a little bit. And those little vibrations on the table from people like pressing on it, writing, actually fluctuates our balances a little bit. It changes their set point a little bit. So keep that in mind as you're working in there, that if a lot of people around you kind of pressing on the table, your number might be moving around a little bit. So try and keep things kind of calm in there. So question 6 says, looking at the sum of the masses, when you added those 5 individual ones together, and your collective mass, how many groups had a different number between the sum that you added and the collective mass that you measured? How many groups had a different number between those two? If they're the same 5 pennies, why are their masses different? Why is the mass different if you weigh them together versus weighing them individually? Why were the masses not exactly the same? Yeah. Well, yeah, it's the balance is rounding, right? Remember we said we had that plus or minus, right? 0.01, right? Well, when you weighed all of the pennies together, how many of those rounding errors did you have? 1. Yeah, 1 mass measurement. You had plus or minus 0.001. But when you measured each penny individually, you had 5 of those little errors. And they add up. The balance is rounding a little up on one, a little down on others. And by the time you make 5 measurements, you might be off by 2, 3, 4 digits in that last decimal place because you're making so many rounding errors. So it says the sum of the masses is probably slightly different. Discuss why you think there is a difference. Well, it's what we call propagation of error. Each measurement has a little bit of error. The more measurements you have, the more errors you're adding together. So again, as we kind of move forward in lab, keeping that in mind, we want to try and make as few measurements as we can so we're not propagating those errors as much as possible, okay? Not always possible, but we try, okay? So the next thing we're going to do is measure volume, okay? And there's a little picture here of a person staring at a graduated cylinder. And what you'll find with any kind of long, skinny glass tube, graduated cylinders, flasks, burettes, pipettes, things like that, is water and other aqueous liquids kind of grab onto the glass sides of that container and they climb up the walls a little bit. And so instead of getting a flat surface across the top of your liquid, you get this curved surface. And that curved surface is called a meniscus. And when you read a graduated cylinder, you always want to read at the very, very bottom of that curve, okay? So when you look at your graduated cylinder, you got your markings on it, right? And here's your solution eye as close to eye level with that solution as you can. That might mean lifting the graduated cylinder up. That might mean you squatting down. Right? Depends on what works better for you. Okay? And the reason we do that is if you're looking up or you're looking down at that curved surface, you get distortions. And it makes it look like it's in a different spot. So we want to be eye level with that liquid level. And we want to measure right across the very bottom of that meniscus. If it's right on the line, we want to put in those placeholder zeros, right? 10.00. If it's in between the lines, we want to make that estimate, right? So what we're going to do is take your 50 ml graduated cylinders, and you're going to put about 20 mils of distilled water in, and that's what the wash bottles are for. We're going to add a little water to those. You can squirt the water in. Doesn't matter if you're right at the 20 mil line. You can be a little above, a little below. That's okay. And you're going to look at and record, very first thing, it says initial volume of water with no pennies in it. So you're going to put in about 20 milliliters. Then you're going to read exactly what the volume is in your 50 ml graduated cylinder. Then you're going to take those 5 pennies you just measured, you're going to slide them into the graduated cylinder, and the water level should go up, right? Because the pennies are taking up some of the volume. And you're going to record the final volume of water with your pennies. Do a little subtraction. That gets you the volume that your pennies occupied. Then underneath that, it says, using your mass measurement from part A, that collective mass, and your volume for all 5 pennies, calculate the density of a penny in grams per centimeter cubed. Okay? So the distilled water is the white tip tap over there. I would say take your wash bottles, fill them up maybe a third, half the way full, because we'll need some water later as well. And then, again, about 20 mils of water into their 50 ml graduated cylinder. Drop your pennies in, record your 2 volumes. When you're done, you're going to go ahead and dump that water out, grab your pennies, and that's what all that paper towel back there was for, was put all the wet pennies on. Okay? So get your water, measure your volume of your pennies, put your wet pennies back in the paper towel when you're done, and then we'll move on from there.
Wait, do we need to do all 5 of them?
Yeah, that's the same thing.
The first one is all.
So when it's like a really long volume, this to the 50? No.
So 21 milliliters.
There.
And then initial volume of 20.
So the precision would be 20 or
What? I think it's
Your volume.
oh yeah. It would be 1 right?
Yeah.
Check 20.
0.1 on that one.
So this is asking the same question then. Feels like it would be more.
It's like right at 22.
Yep.
You said it like that, if you volume up to 510.
22, yeah.
Right. So when you do your so your volume is your final minus initial. That's the volume of your pennies. So determine total volume of pennies and record the volume. So the volume would be 2, and then your collective mass is here when you do your density.
Got you.
So remember, if this goes to plus or minus 0.1, all of these values should have at least 1 decimal place on them. So if you were right on the 22 line, it was 22.0.
Okay.
Around a 20 line, it's 20.0. Right? Because if this is capable of being that estimate to the 10th, to the first decimal place, we can make sure all of our measurements are recording to that first decimal place.
So in the case of this, it's like right above the line. Should we actually put 22.1?
So if you look at it, so there's, so if you look at this right at eye level, there's 20, right? There's 21, there's 22. Right. So your meniscus is just below 22. Right? So if we're looking at the very lowest spot, okay? So remember when you look at this liquid level, this almost looks like a lens up here. Right. Right? We don't want to measure that part. We want the very, very lowest part. So it's clear. And we get that sort of weird spot at the top. We want to measure the very bottom of that spot, okay? And if you look at yours, right at eye level, you're just below the 22 line. So you might want to call that 21.9, 21.8, something like that. Okay? So keep in mind, right, the precision of this 50 mil graduated cylinder was to the 10th place, right? Plus or minus 0.1. Means every measurement we make with that graduated cylinder should be recorded to that first decimal place. So if you had exactly 20 milliliters of water, you were right on the line, it's not 20, it's 20.0. You get that extra digit, right? Remember we're talking about significant digits. If our tool can measure to the first decimal place, we need to make sure we're recording to the first decimal place. Don't drop those digits, okay? So once you've got your volume, let's do a little subtraction there between final and initial, that'll get you your volume. You can calculate density. So density is just a ratio of mass over volume. The mass that we're going to use is that collective mass when you weighed all 5 pennies together, and the volume is the volume you just measured. Okay? So volume or density can either be in grams per centimeter cubed or grams per milliliter. 1 milliliter and 1 centimeter cubed are interchangeable units. They're equivalent to one another. So it doesn't matter which one you use. Okay? So go ahead and calculate the density for your pennies by taking your mass and dividing by your volume. Exactly. Because since it's a subtraction, you're subtracting and we go to the place value, so you get to keep that 0. Yep. Okay, so if it's a division problem, the division rule says total number of digits, so we have to round to the least number of digits we had in our original answer. Yeah.
Alright, so as far as like,
Okay. So you're gonna take your mass from here, and you're gonna divide it by your volume from here. The collective mass, yeah, so that mass you had over here, that collective mass. So here again, if this tool, right, can go to the 10th place, then these measurements should also go to the 10th place. So if these are 20 and 21, they're really 20.0, 21.0. Their final volume is 1.0. So you get that extra 10th place. Just think about it, if you'd been a little above the line, you might be 20.2. You're a little below the line, it might have been 19.8, but you get that extra digit. Okay. All right. Okay. So you're, I think you've got those two values. Your final line would be 21. But so the precision here is the distance, right? So I can estimate between them. So my precision is the plus or minus 0.1. I
think I did it wrong.
Okay. So when I measure this initial line with 20, it's really 20.1. 20.0.
People that were
Right on the line.
Wes, and there's one 20-year-old.
So when you do the subtraction, you have 1.6
Oh,
as your volume.
he used to work there. He quit.
So should I tell my buddy like to apply there?
Yeah, he wants to. He's looking for a job, but they're hiring to indefinitely.
Divide it by your volume.
Doesn't matter. No, he was a trainer, or not a trainer, a salesman. But like his best friend, like our best friend Cody, he was like that. And everybody was like really chill. And like they demoted him, even though he was like hard working right there. So we just got like
He was there before the
no, he just got demoted for no reason. No. Cody, the guy who's GM, but Matt quit too yet.
It's a 6.3 divided by 4 by 3 plus
Well,
Okay, so just a little example sort of how to do this.
alright.
Your volume measurements that you recorded should have a 10th place number on them. If I was right at 20, it's 20.0. If I went up, in my case, I'd said 21.8. But if I call that 22, I'm going to call it 22.0. I'm going to get that decimal place. Then our subtraction rule says we go to the place value. So if each of my original values goes to the first decimal place, my answer does too. So my answer would be 1.8. If you had 20.0 and 22.0, your final answer would be 2.0. You get that value, right? Then we're going to do our density.
Pretty sure I did it wrong.
So if I say my collective mass volume was 13.138 grams, and my volume is 1.8 milliliters, I'm just going to plug that in my calculator and do that division. Take my collective mass divided by my volume. Okay? So in my case, I do that. I get 7.29888888, whatever, right? So what's our rule for multiplication and division when we're talking about significant digits?
Smallest amount.
Smallest amount. My mass number has 5 significant digits, but my volume number only has 2. So my final answer only gets 2 significant digits. I can't have an answer that's more precise than the measurement I used to get that value, right? So I get the 7 and the 2. Because there's a 9, that becomes 7.3 grams per milliliter, or 7.3 grams per centimeter cubed. Exactly the same, they're interchangeable, okay? So your masses and volumes and densities are going to be slightly different, right, based on your numbers, but that's kind of how we want to deal with that value. Doesn't it seem like kind of a waste? We had this 5-digit mass, but we only had a 2-digit volume. We had all this great precision in our mass, and we lost it, right? So what could we do differently maybe to increase that precision a little bit?
Use the 10 milliliter.
Use a better graduated cylinder maybe that we could get some more precision on. Unfortunately, our 10 mils are really skinny. Can't get a penny in there. It doesn't work, right? But any kind of, if we could maybe get a more precise volume, we could get a better density number, okay? Number 9 on there is about converting that unit. And we'll go through that in a little bit, but I want to make sure we get through all the data collection first. That's something we can do a little bit later. Question? What is the question on the conversion?
I do have a question.
Okay.
How do you get the grams centimeters?
Okay, so the unit of milliliters and the unit of centimeters cubed are interchangeable because 1 cubic centimeter and 1 milliliter are the exact same volume. So we can just swap those 2 units out, one for the other. They're exactly the same, okay? So even though our graduated cylinder measures in milliliters, we can also call it centimeters cubed. It's exactly the same. And like nurses call it cc's, cubic centimeters, same unit, okay? All right, so we'll come back to that conversion in a minute. All right, next we're gonna have some fun measuring water, okay? And this is about density and volume and things like that, okay? So we have an issue with some of our glassware. If you look at the top of the graduated cylinders, and those of you with bad eyes like me might need to get pretty up close and personal with it, but at the very top, right where like the name of the manufacturer is, you're going to see 2 tiny little letters. They'd either say TC or TD at the top, okay? Some graduated cylinders that are labeled TC, that TC means to contain. Means if you put, 5 mils of liquid up to the 5 mil line in that graduated cylinder, it's holding exactly 5 milliliters. But what would happen if you poured that out? Would every single drop of water come out of that graduated cylinder, or would some be left behind? Yeah, some would be left behind. So that's what the other kind of graduated cylinder, the TD means to deliver. Means if I go up to 5 mil line on a to deliver graduated cylinder, and then I pour it out, it dispenses exactly 5 milliliters. So they have different applications, depending on if we want to transfer that volume to another container, or we want to hold that volume in the container that we're using. So we have all different kinds of TC and TD graduated cylinders. So we're going to sort of measure how accurate our graduated cylinder is. And we already showed that volume measurements usually have a lot less accuracy than mass measurements, because our balances just have more precision to them than our graduated cylinders. So we're going to use that to our advantage here. Okay? So we're going to look at our 10 mil graduated cylinder. We already sort of figured out what its precision is, right? It goes to the second decimal place. And we're also going to measure the temperature of our water. So there's some thermometers back there. Just put the thermometer right in your wash bottle. Let it settle. Read the temperature off. Okay? It says what's the precision of the thermometer. Right? So we're going to look at what the markings are and figure that out. And we're going to determine the mass of a clean, dry, empty 10 mil graduated cylinder and the mass of an empty 50 mil Erlenmeyer flask, and record those in your table. So your little triangular flask and your little tall skinny graduated cylinder, take them both into the balance room, make sure the balances are reading zeroed, put that empty graduated cylinder on there, record its mass, put the empty flask on there, record its mass. So those are the first things I want you guys to do. Get those two masses, get a thermometer, record the temperature of your water, and then we'll go on from there, okay? So, again, back to the balance room to measure those masses. Thermometers are on the back counter by the pennies. Just drop those in your wash bottle and then record the temperature of your water.
What about the number 9? I have 38.095.
What was it now? Sorry.
38.095. Good?
You got the paper, right? You grab it.
No, you're fine. Is that it?
Yeah.
Start off with a nice little camping, then you start with air in and gas and change the color of the flame and change the height of the flame. Learn how to use it. First thing you gotta do is close the bottom of the Bunsen burner. You gotta turn the gas on full.
Then we go back, let's fill with water.
What is the precision?
Do the temperatures, whatnot.
Gas on full.
Like 22. What do you think?
Go between 1 and 0.
And we have to estimate.
Where's that?
Or 21.5. Would you think okay, so and then observed volume of water.
5?
1, 2, 3.
So do we do the temperature of this one or that one?
I think just in there.
Right now, what we're doing is measuring the temperature of the water.
Four, measure volume, you need a graduated cylinder. Or pipette, we don't got pipettes in here. These are just glass, not going into place. Not measure volume.
I don't know. I guess we would. We still have the.
Temperature or observed volume of the water.
And we want the bottom of that plane. Envelope to the bottom.
Or we just measure?
What is the? How long did you learn how to do that? I don't remember. I think she said
So how much are we supposed to pull the graduated
Pull it in, get it close. Move the experiment to where it's coming from.
Okay, so the next thing is to fill it. Yeah. And we have to estimate the last one, right? 23 points.
So what do we have to
The water.
Oh, because we pour the water from the graduates.
I feel like we observe volume of water in the 10 milligram cylinder.
Yeah, I think so.
And
The
then
precision of the thermometer will be plus or minus 0.1, right?
no, it'd be 0.01 because it's the same as
Oh, okay.
this.
Yeah, if I can't switch with Phil,
So then, I guess we just measure the mass. Is that what this is?
In grams, yeah.
Yeah.
okay. So I just
But we
highlighted on the
didn't-
data table where you guys should have numbers right now. So you should be measuring the temperature of your water, you should have your mass of your empty graduated cylinder, and the mass of your empty flask. They're kind of weird spots on the table. But make sure you have all those numbers. Okay?
Yeah.
So once the thermometer's been in the water for 30 seconds to a minute, it should equilibrate pretty quickly. Go ahead and record the temperature of the water
You really mess around.
on there.
You work at Cool.
Let me know what you think.
They used to bust water bags, but only work 3 days a week. Lady serves there, so show situation. No, my.
So make sure you record the
Serves there.
precision of the thermometers, and then you accurately record all the digits you get on your temperature, okay? So you should have the first two, precision of the cylinder and the thermometer done. You should have temperature of your water, and you should have your two masses done. Okay? So now we're going to move on to the next part. We're going to use the wash bottle to fill the graduated cylinder to as close to exactly 10 milliliters as you can get, okay? If you need to pour out or add a little bit more, we want to try and get so that you are at exactly that meniscus right on 10.00, so that when you get to this line where it says observed volume of water, that observed volume of water should be exactly 10.00, because that's what we think is in that cylinder if we're right at that line. Okay? So I want you to use your wash bottle, squeeze in there. You can usually get that dropper to get you like 1 drop at a time. Try and get as close to exactly 10 milliliters as you possibly can.
That's pretty good.
You could do that.
I enjoy going there.
So 9.99 would, so you have your water in here, because you're going to weigh it in here. Oh, you already did all that, and you poured it in here and weighed it in here? Okay, that's fine. Okay, so once you guys have exactly 10 mils of water in your graduated cylinder, you're going to take your cylinder and your flask, you're going to go back to the balance room, you're going to weigh the graduated cylinder with the 10 mils of water in it, you're going to pour that water into the flask, and you're going to weigh the flask with the water in it. That's going to go mass of graduated cylinder and water, mass of flask and water. So you're going to get both of those measurements. Once you have those, do subtraction, get the mass of the water in both cases. Okay? Yeah. Sure. Okay.
So 60.642.
No, okay, you can't do that. The whole point is we're dispensing the 10 mils of water. Okay, so then this mass is bad. Take this out, and what I would do is if there's any little water droplets in there, just weigh it as you can, because there's no water droplets in there. Pour the water from here to here, and then weigh it. Okay? Because it's important that we get the exact same thing as the water. That's also why you're not. Alright. So why you're gonna dump this out, there's more water than you need. Right. Also, if there's water droplets in there, just weigh it with those little water droplets. Exactly. Right at 10.
So first let's measure that one. This, okay.
Yeah.
So let's see, graduate.
59.84.
Yeah.
1, 2, see that? 37.744.
Yeah.
437.
Oh, whoops. Yeah.
So I was laying two.
And then we pour the water in here. 40. Wait. Okay. Yeah. And then to get that in, so it's 744. I know. Okay. Okay, that's good. So now we pour the water.
So 0. Yep. Yeah, make sure you have all 3 of those decimal places on there. Yep.
Okay, then.
Get in there.
And then we just subtract.
It's always one less than the right? So these markings are every 70, 71, 2, 3, 4, right? So you can always go
Have to
one
do school and work.
past the markings.
Really?
So markings are
Yeah,
only
that would be
one.
annoying. Just like me.
Okay, so
Yep.
this one is 10.
Yeah, I was gonna
Exactly.
tell him to schedule me Wednesday,
Yep.
5 o'clock shift. I would be like, come here.
Okay, so once you have those masses, again, do that little subtraction. Figure out what the mass of your water sample is in both the graduated cylinder and the flask. So, once you've done that subtraction, we're down at question 13 now, very bottom of the page. It says the mass of water in the 10 ml graduated cylinder is probably slightly different than the mass of water in the flask. Why do you think that happened? Why do you think there's one mass of water in the graduated cylinder, poured it in the flask, and there's a different mass of water? Yeah. Some of the water got left behind, right? You didn't transfer 100% of the water. Some of the water got left behind, so the mass is different. So now we go to the top of the next page. And it asks, are the masses of the water in the data table more precise than the precision of the graduated cylinder? So your graduated cylinder was plus or minus 0.01. Are your masses more accurate than that, more precise than that? In other words, do your masses have more decimal places than your graduated cylinder? Yeah, they do. So one of the things we can do is, as long as we have a more precise tool, we can kind of see how accurate our other measuring tool is. So since our masses are more precise, we can use those masses to figure out the accuracy of our 10 ml graduated cylinder. So that's kind of where we're going here. So we're going to use the density of water to determine our accuracy. And water, like most other substances, changes slightly as the temperature changes. So you have a little table of values there of density of water at different temperatures. So find the density of water that's closer, the temperature that's closest to the temperature you actually measured. Did anyone measure a temperature less than 22 degrees? Okay. So I've got densities for the other temperatures. So
Yeah, but it's 21.9, so it's not use
21.5, 0.997882, 21.0, 0.997992, 20.5, 0.998099, 20.0, 99820. Okay? Hopefully no one was less than 20 degrees, otherwise we have really cold water. Alright, so find the density of, find the temperature that's closest to the temperature you measured, and find the density of the water. Okay, so on your next data table, just have on that next page, we're going to transfer a little bit of information, okay? So where it says mass of water, this line right here where it says mass of water, you're going to put in your masses from the previous table. Okay? Mass of water in the graduated cylinder, mass of water in the flask, density of water off the table, whatever's closest to the temperature you measured, same density in both boxes. Okay? So take your two masses from the previous page, transfer them over.
Of just the water?
Just the water. Just the water by itself in both of those things. And then the density of water from your table. So what we're going to do now is we're going to take that density equation and we're going to take that we have a mass and we have a density and we're going to use it to solve for the actual volume of water that was in our graduated cylinder and in our flask. So we need to move this equation around a little bit. We need to solve for volume. Volume equals mass divided by density. Okay? So in the table here, where it says calculated volume of water, show your work, we're going to do that density equal, or volume equals mass divided by density. Take the mass of your water, divide by the density of your water, and then it says calculator answer including all digits, and then the significant digits answer rounded appropriately. Okay? So you're going to take the mass, you're going to take the density off the table, mass divided by density gets you volume, you're going to show that work here. You're going to give calculator answer, that includes all the digits your calculator spit out at you, and then your answer with the appropriate number of significant digits. Okay, you all understand what we're doing here?
Oh, yeah, that was me.
Oh, okay.
Just wanted to make sure.
Let me do this on the table.
Go ahead.
So, anyone who might be a little bit confused with what we're doing, I did a little sample one here. So I said if my mass was 9.983 grams, and my density was 22 degrees, 0.99777, I do that division, this is what my calculator spits out. 10.00531185. Remember our division rule says my answer can only have a certain number of digits, right? 9.983 has 4 significant digits. My density has 6, so I only get 4 digits in my answer. So my 10.00, that 5 rounds up, so I get 10.01 is the actual volume according to my measurements. Yours might be a little different. If your mass number up here was 10 something, you get 5 significant digits, because 10 point whatever gives you 5 digits instead of just 4. Okay? So you should have show your little calculation, calculator answer with all the digits, and then the answer rounded to the right number of significant digits. Okay?
Every other day, 9 to 5.
Oh, okay.
Saturday.
Sharing your calculator.
I'm like 6 days a week. Saturday I'm off. Usually like a 9 to 5 or 2 times.
Right. Yeah, so since your mass number had 5 digits, you actually get 5 digits when you round. You get 10.106.
I'm like in my own
Because it's a 4, you just drop it, so 10.106.
be annoyed by the customers or like the manager. They just like let me
So this now should have a lot of digits. Okay? So you went here, you don't round that way. Okay? So you're doing a subtraction, you have 3 decimal places, 3 decimal places, you get all 3. So don't round those away, okay? So this number here should be 9.672 and 9.536. You get those digits. So when you come down here, that instead of 3, you have 4 digits up here, and you get 4 digits down here. You get that extra little bit of precision, okay? Otherwise, math looks good. Just change those numbers, which is obviously okay. Okay.
I would.
Observe like, oh, that's how much your graduated cylinder says that you had. So we would read that as 10.00.